What's up, guys? Morning, afternoon, evening, wherever you happen to be. Hope you're having a good day so far. I see that it's 2:30 UTC, so let's get started. So my name is Samarth, and I'm the president of the Heart Tech Fund, and along with Linda Huang, Blake Edinburgh, and Kirk McGregor, we spent the last few months trying to put together this symposium and see how we can best help the Hyperloop community, especially due to the lack of competition from SpaceX this year and the coronavirus pandemic. So we are extremely excited to have seen the interest in this event and to make it happen. And we would like to first start by thanking all the researchers for all the work that you put into this and for the presentations that are coming up. So Cooper Hyperloop, Helwan Hyperloop, Hyperloop IATB, HyperExcite, and OneLoop. Thank you guys for taking the time to write those papers and to submit them for this weekend's submissions. We also want to thank our stakeholder organizations who are helping to vote for the top teams and take part in the discussion for how Hyperloop should move in the future. And this weekend stakeholder organizations are ACOM, MIG Hyperloop from South Africa, as well as Virgin Hyperloop One. So look out for them on the Slack and look out for them on the Zoom, and looking forward to some great conversations. So the first thing I'm going to go over is just kind of like what we're going to be doing today. So today is going to be a day of lightning talks. So essentially each team is going to give a 5-minute talk within the session that they submitted to about the research work that they're doing in that area and what are some conclusions that they got from that. So what we're going to do for Q&A is if you have any questions for any of the teams and you're a stakeholder or a researcher or attendee who is on the Zoom, please put your questions on Slack just so that all the questions and all the discussion is recoverable after the event. So we're going to have the Q&A session at the end of all sessions. So that'll be around like 4 p.m. UTC. So how it's going to work is the top ranked questions. So the questions with the most thumbs up on Slack are going to be the ones that we ask the teams at that time. But I mean, it's a Zoom meeting, so feel free to stay on if you wanted to have further discussions or whatnot, or to message each other if you have any follow-up. All right, so voting. Right, so the reason why we did this 2-day setup was because we wanted to have talks on one day, and we wanted then talks to then percolate into discussions on the second day. So tomorrow is when we're going to have a set of discussions on the topics that we're presenting on today. So we can talk with each other about how we're going to build the future of these areas. So the teams that are the top ranked teams today are going to be the ones that moderate the panel tomorrow. So that's basically like so the team really has the floor at that point. The team that does really well today, and how they will do well today is if their presentation is good, people vote that their presentation is good on our website, one of our polls for that section, as well as their paper being really good. So we're going to take both of those things into account when helping make that decision. All feedback from all of the stakeholder and research organizations will be posted later tonight as well, so that each team can see exactly what people were saying about them and what was the reasoning behind it. Yeah, the polls are both live right now on hearttechfund.com/hyperloopvoting.html. So if you want to vote, or if anybody else who's watching wants to start voting right away, go for it. So yeah, that's pretty much it. Picking teams today, listening to teams today, panels tomorrow, have a fun discussion, and yeah, hope some good things come out of it. If you have any questions at all about the event or any formatting, please feel free to send a message on Slack or on here. But without further ado, let's begin. Let's have our first talk of the day. The first talk of the day is going to be, the session is going to be on propulsion, and Hyperloop IIT Bombay is going to be presenting that. Fennel, Hyperloop IIT Bombay, are you guys ready?
Okay.
No?
All right, so it seems Fennel is not here. So
Okay.
Zabir, I'm also part of the team, and I'll start the presentation.
All right, go for it. Please share your screen.
So I hope my screen is visible now.
New induction.
You're looking to present?
Hello. Yeah. So I'm about to present. Just 1 second. I just want to check if our presenters are ready, so they can begin talking.
Sure. Sorry, I thought you were just looking for the button.
Okay, I'm so sorry. Just give me 1 second. I need to make sure that I get everything correctly before I start. So sorry.
No problem, no problem.
Automatically.
Yeah,
Okay.
make sure you like mute if you're not talking, presenting.
Okay, so may I start? Yeah? Fennel?
Sure.
Yeah. Okay, hello everyone. We are here to present a paper titled Design of Linear Induction Motor and Electrodynamic Levitation for Hyperloop Pod, representing Hyperloop IITB from Indian Institute of Technology, Mumbai. From the title, it's clear that we will be explaining our design approach for LIM and the levitation system design to support its seamless working. So first, looking into the propulsion system, we have the linear induction motors. An LIM is a linear alternate current motor designed to produce thrust instead of torque. Unlike conventional wheel-driven vehicles, LIM and other levitation-based linear motors can operate at much higher speeds, making it an ideal candidate for Hyperloop, which requires about 760 miles per hour. That is the motivation of our team to design an LIM. The first issue we had to tackle was the levitation requirement for contactless propulsion. Our levitation system, which will be discussed, is designed to lift a pod of 400 kg at speeds slightly higher than 10 meters per second, that is 22 miles per hour. But to reach that speed, we have decided to use a BLDC motor. We initially were working with the idea of double-sided LIMs, but eventually landed on single-sided LIMs for our first prototype. We are using double-layer windings and three-phase high-voltage AC from a custom inverter, which should handle the high-voltage DC input of about 700 volts from the battery pack. It should also have high frequency to decrease the size of LIM needed to propel the pod. So mounting of the LIM on the chassis has to accommodate the complex wiring and the air gap requirements, and these details are being worked out in collaboration with the structures team. So moving on to the simulation part, these images show our initial double-sided LIM and the contour of magnetic flux density from COMSOL simulations. Since then, we have moved to the current single-sided LIM with 24 slots, which is about 1.6 meters or 6 feet long. These simulations are being carried out to optimize the cruise speed and the current input using parameter sweeping. Now, coming to the levitation system, which does the job of levitating the pod. This is an important step because this reduces the drag on the pod, which in turn can improve the speed. The system requirements of levitation are as follows. It should provide a stable levitation, that is, the air gap fluctuation should not be high. It should be cost-effective, fail-safe, and wear-resistant to minimize maintenance costs. So, considering these points, we chose the permanent linear Hall-back arrays to do this job. One of the main reasons is its passive nature. Hence, it's completely fail-safe, along with requiring zero power. Now, coming to the relation between levitation and propulsion. The vertical air gap variations would result in fluctuation of thrust by the LIM, hence these are to be minimized. The levitation system should have little drag and high lift-to-drag ratio at all speeds, so that the propulsion system need not waste power countering the drag. The thing we are currently working on is the modification of current passive levitation system to a combined array of electromagnets and permanent magnets, so that control is increased, ensuring better comfort. So these are the simulation results of our pod's levitation system. You can see the lift and drag profile of the pod with the x-axis being velocity and y-axis being air gap. So from this we can see that the air gap would keep increasing and will saturate at a later stage from the lift contour. And from the drag contour, we can see that the drag keeps reducing as the pod moves faster.
Next up, we have electrical dependencies. So a complicated propulsion system like this requires a power system which is designed for safety, workability, as well as dependability. So the onboard power supply comes from an accumulator system of 15 packs with 13 LFP pouch cells in each. Thus, maximum voltage is 712 volt, and a DC-DC converter ensures stable 12 volt supply. This powers the propulsion system as well as a control system which helps to communicate the pod state outside, as well as ensures that all the onboard computing gets all the sensor data properly. For electrical safety, which is a major priority, we use a shutdown circuit which is controlled by certain signals defined as system critical signals, and we have PCM-based cell cooling for all the cells. Thus, this concludes a short insight into Hyperloop IITB's pod system, and thank you, and feel free to reach out if you're interested.
All right. Thank you so much to Hyperloop IIT Bombay for your presentation and for the work that you put in. And yeah, please leave any questions on the Slack. Next up is going to be OneLoop from UC Davis to talk about their propulsion system. OneLoop, you have the floor.
Hey, Samarth. Thanks. I wasn't sure if Mira, do you want to take over or?
I mean, you if you want to present on propulsion, you definitely know. Yeah, that I'm.
I don't have slides or anything, but I would like to say a few words. If you want to go first.
Please.
Okay. So hi, my name is Ryan Parker. I'm on the power team, and I didn't really see a power section, so I thought I would just say a few words here. But I'm essentially the co-lead, and we're developing the custom inverter circuitry and the battery circuitry. But again, the inverter circuitry has to work closely with the power or the propulsion team, because the characteristics of the limb and the final velocity of the pod are very closely related. And OneLoop intends on building its propulsion inverter in-house, and we are currently researching and doing tests for spinning up our own limb core.
Okay, so would you like to continue presenting or would you like me to?
Oh, go ahead. Take the
All right,
floor.
awesome. Sounds good. I will share my screen. Mhm. Okay. There you go. All right. There you go. Backwards. Okay. Can you all see my screen? Hello? Can you? Okay.
Yeah, we can see it.
Awesome. So, all right. So our three leads, Aaron, Jason, and Michael, unfortunately can't be here for the limb. So I'm just going to go over how our limb works. So in the past, we used cold gas thrusters for our linear induction motor, which is recommended by Elon Musk, and we did quite well. This year, however, we are planning on using a linear induction motor. They have been proven by maglev trains, which are used widely throughout the world, and they're likely the best option for a longer track. So while cold gas was a very good option for a shorter track, we're moving to a limb this year. So unfortunately, due to COVID, we can't really test in person, which is unfortunate because we need a test drive. So we're probably going to get to testing in around September when our new facility opens up. We will obviously have social distancing enforced. But right now, our main plan for the future is get some physical testing done. So our limb, the way our limb is working for now, and we're fairly certain we're going to stick with this plan, is we're probably going to use a D limb. So it's a double-sided limb. This allows for more lateral stability in the pod. It also, we're planning on using the limb as brakes, possibly. We have a separate braking system, and we're considering sort of possibly using the limb in addition to, in complementary fashion to the brakes, or possibly just as brakes on their own. Within each limb, we have a full double layer, and we have 3 limb sunsets for better overall performance. So we have, again, we're still working on the more technical details of the limb, but this is what in our simulations, this is what has come out as likely the best and most efficient system for our linear induction motor. So we decided to use ANSYS for our simulations. This is because it's widely used among professionals and professors in the industry. And we have 3 main ways in which we're testing our limb. We're using ANSYS, we're using mathematical models, and we're supposed to be using physical simulations, but we can't really meet in person. So we're really just using ANSYS and mathematical models at the moment. If you attempt to use ANSYS at any point on your pod, we recommend testing the mesh to find an adequate level of accuracy and reducing difficult geometries. One of the biggest challenges we faced in ANSYS, other than the fairly steep learning curve, is that it tends to be very, it tends to take a while to run. And we as a team only really have our laptops. We're looking for high performance computing solutions, but right now we're still using laptops of our team members, and we have to compromise on the mesh. Obviously, we want to be as accurate as possible, but this can take up to over a day to run. So the testing overview. Testing is probably the most interesting to those of you who are, well, unless you're very much interested in ANSYS like I am. But we have a lot of testing that we're planning on happening in the future, probably around September and later on. Then we have a test stand. We have a dynamic test stand which we're hoping to use. We've used in the past. We have our objectives for testing are obviously verifying that the limb can perform safely without undergoing any rapid spontaneous combustion, which would be bad. We're testing to make sure the motor has thrust, the wire ampacity, the thermal response, the magnetic field leakage, and obviously the vacuum capabilities. So we have a lot of tests that we're planning on happening, which you can see. One of the one of the tests that we're planning on probably doing first thing when we get in, it would be the static motor torque test, which would definitely tell us if we're on the right track in terms of how we're designing the limb. So thank you. That is all for today. Hope you guys enjoyed it. All right.
Awesome. Thank you so much for presenting Team One Loop on your propulsion. Now we're going to go to Southern California and Team HyperExcite from UC Irvine. HyperExcite, you guys have the floor. Please show us what you did.
Hello, I'm David Villapando from UCI HyperExcite. I'm the dynamics lead.
Yeah, and I am Myron. I am the chief engineer from HyperExcite as well.
All right, Myron, are you ready?
Yeah, give me a moment. All right, so yeah, just to introduce our team a little bit, HyperExcite was established in SpaceX Hyperloop competition, was first introduced in 2015. And since then, we have been focusing on designing a small scale prototype with a new dynamic and braking system, specifically propulsion system. Our stabilization didn't change too much this year. And compared to last year's design, 2018 to 2019, this year's pod is much more smaller and cost effective because due to our situation and lack of competition, we didn't seem that it was feasible to build a full scale pod anyways. Next slide. So first, yeah, we'll be introducing a little bit of our propulsion. This year we decided to switch up to a gearbox design, which is a lot different than what we usually go for. We saw that most of the top teams usually went for either like a limb or like a gearbox design of some sort. We felt that a gearbox design was more feasible at our scale. So that's what we decided to go for. And we will have DJ introduce that.
So just going over the layout of everything, in order to reduce costs, we ended up mirroring as many components as we could in the topside stabilization and the propulsion. So you can see this topside stabilization. We have 2 of those units and 2 propulsion units that go at the top of the flange of the I-beam. And then we have 4 underside units to go underneath the flange of the I-beam to clamp, and then 4 lateral stabilization units to keep the pod centered on the I-beam. And to go into detail with the propulsion, in order to keep it compact and costs within our budget, we're using a dual motor system with, those are skateboard motors, 190 kV rating, and a pulley belt system in order to drive the drive wheel. We're also using tension springs as suspension and dual directional dampers. The unit's intended to be mirrored to reduce the number of unique parts that need to be manufactured and just reduce our overall cost. And it's also meant to be modular, so this whole thing can be removed with about eight bolts. So that way we can easily maintain and adjust things, adjust pre-tensioning on things. As for performance, we haven't actually been able to get in the lab and manufacture due to current events, but our best estimates that we could create is that on the 20 meters of test track we have available, we can reach approximately 8.9 meters per second, which is about 20 miles per hour. So that's our propulsion system. Thank you.
All right. Thanks, Team HyperExcite, for presenting on your propulsion system. Up next is going to be Helwan Hyperloop. So actually, they're going to present first about their propulsion, and then we're going to move into the pod control system, and they're going to present about their their
Okay.
pod control. So just a quick reminder before you get started, Mohammed, like the Slack channels are named so that like the name of the team, each team has their own channel, and
the whole
then
team?
there's the
Okay, okay, I will send it. I will send it. I will send the name of the team, of the whole team.
I already made one for you. I already made one for you. So if you have any questions, just put it in there, or put
Okay.
it on the chat. But yeah, go
Okay.
ahead. Why don't you tell us about your
Okay.
propulsion system?
Okay, thank you.
Mohammed, you ready?
Okay, I'm getting it ready.
Oh, okay, okay. Just wondering. Thanks.
Okay. Is it clear?
Yep.
Hello? Is it clear? Yeah. Our propulsion system, first I'm Mohammed Hisham, propulsion system designer in Hyperloop. In the first, our targets in the year was the speed to reach the maximum speed of 200 km/h, and our weight to be 120 kilograms by calculations of the whole team systems weights. In the selection, we have many choices: axial compressors, linear induction motors, or brushless DC motors. For the powertrain forces, we have calculated it. We have calculated the powertrain forces: traction, acceleration, aerodynamic drag, and rolling and rolling resistance forces. And the total force was 1,260 Newton. And depends on the considerations of the selection. We have the cost and the lead time in the season, and the availability in our Egypt markets, and the SpaceX competition rules. We have selected the brushless DC motor with 82 kilowatts. And our were 5,000 RPMs and 140 Newton meter. And the transmission ratio was 1.2. For our driveline selection, we have considerations like cost and simplicity of the system, RPM and torque, and we have selected the driveline belt drive of the belt to drive. And our mechanical parts like shafts, couplings, and pulleys in the driveline system we have tested it and simulated on the ANSYS finite element analysis, and this is the photos of the simulations of the stress equivalent stress. And this is our final propulsion system assembly. Okay, thank you.
Thank you so much, Mohammed, for your presentation. Next up is going to be Mahmoud and the controls team at Helwan Hyperloop as we transition into the pod control session. Mahmoud, the floor is yours.
Thank you. Good evening, all. Let me introduce myself first. My name is Mahmoud Nasser, control team head at Helwan Hyperloop. Helwan Hyperloop is an Egyptian team that has been established this year with a goal to design a Hyperloop prototype to participate at SpaceX bot competition. IoT, how the internet starts. There were many devices connected to each other over a local server. Then the number of devices increased, so the internet appeared, and the devices got varied. Now we have Android mobiles, iPhones, tablet, laptop, and many more. So all these devices called things and connected to internet. So the name of Internet of Things appears. There are many applications for Internet of Things in our market, on our life: smart parking, connected cars, and vehicle tracking, and so on. Our system structure, we will start from bottom to up. Firstly, onboard sensors. In order to have a robust system, different sensors have to be distributed around the board. Measure all parameters, which the decision will be taken based on their values. Then system controllers, they are microcontrollers for each system to take sensors data and make actions based on it. Then our onboard computer will act as the brain of board that all systems connected to, and monitor their performance and also interact with them if there is any problem happened. Sensors on board, there are an important parameters that should be measured, like distance, temperature, stability of the board on I-beam. So all of these values will be measured. System controllers, there is a controller for each system to manage and control it. For example, the navigation system is measuring the distance traveled by the board in many ways using incremental rotary encoder and fluorescent sensor, and send all these data to all systems and know how the current state is. We will use Node MCU for its advantages, integrated ASP chip, and supporting TCP/IP protocol, which we will see how we will use it next. Now we know how the systems work, but how they will communicate with each other. It's time for M2M or machine-to-machine concept. It's the way that devices communicate with each other. M2M is divided into two main categories. First one is local M2M, which all devices connected with each other locally, but I want to know what's going on. So we build a local web server that connected to them, to system controllers, over a MQTT protocol, which is a light protocol suitable for small data. The MQTT protocol make a MQTT broker, which acts as a virtual wallet to store data from all devices. All clients that connected to MQTT broker send the data to it and it store data, and all systems could access data at any time. So we build our dashboard to display all system data, and also could interact with the bot through it manually if there is any problem happened. For emergency, we connected our critical system to an IoT platform, also to be in safe side and communicate with our onboard computer, which is Raspberry Pi, in remote desktop access mode using port forwarding. We're trying to apply off-board diagnosis with using MATLAB Simulink and Raspberry Pi and Amazon Web Service. We build our mathematical model for our bot which is running into the cloud, and also the Raspberry Pi, which takes all data input and output from the real environment and send it to the cloud, which running the model for our bot, and compare the data comes from the physical asset to the data from the model and take the decision based on this data. Thank you.
All right. Thank you so much, Mahmoud, for presenting on your control system. So we're going to take a few minutes break before starting with OneLoop's presentation on their propulsion their power management system, sorry, and what they're thinking about doing for batteries and whatnot. So at this time, please, if you haven't already gone on the Slack, please go ask questions to the teams. They really spent a lot of time to put all of this work together, so please leave any good comments as well. And yeah, see you guys at 3:10 UTC. And if you have any questions, just like ask them. Any like immediate questions, just feel free to ask right now.
ايه يا اسطى شفت العبط؟ يا اسطى شفت انا مش عارف اتكلم يا اسطى. اه يا عم ده انت قعدت سنة عشان يفتح. اه يا اسطى. ايوه ما انا يا اسطى النت زبالة. اه يا اسطى حاجة غريبة.
Hey, Mahmoud, were you saying something?
يا اسطى انت ما سمعت اساسا البرزنتيشن بتاعتي؟ اه يا اسطى عايز انجز.
Sorry, do you have a question, Mahmoud? All right, welcome back, everyone. Hope you had a good break and see some good discussion happening on the Slack. Now we're going to go into the power management and section on batteries and whatnot. OneLoop, you said you would present at this time. OneLoop, you have the floor.
Hey guys, I think this is me. So my name is Ryan again. I'm the power electronics guy at OneLoop, and I'm really happy to be talking to you today about our power system. The past 6 to 8 months, I've spent a lot of time researching the induction motor system and the battery management system for the pod system. And it's sort of been a passion of mine. And basically my biggest focus was researching the power electronics that go into driving a 3-phase linear induction motor, because that's probably the most significant part of this whole competition. And after a few months, 2 months was our first prototype, it managed to spin up a limb. It was awesome. And our second prototype has just finished. I finished it like a week ago and sent it off to a design system or an electrical engineering firm for review. But basically, we're building a huge inverter system to pass maximum current through the limb to go as fast as possible. And we're designing the limb with the propulsion team as well to get this done. And the other extremely important part of our power system is the battery management system. And so I've also been researching all the safety features that go along with that as well. Now, I don't have pictures, but essentially I could just show you the BMS that's in a legit Tesla, all right? It's based on the same integrated circuits, and it has additional temperature sensors to match SpaceX requirements. It has cyclic redundancy checks in all serial communications with our PLC to ensure accuracy. And we're planning on using very sensitive closed loop Hall effect current sensors to know the pack current at any time. And in the event that the current is, unacceptable, we have isolation relays on both pack terminals to completely isolate the power pack. Finally, we also have fusing and an insulation monitoring system to detect if anything has gone wrong in our insulation to make sure there's no short circuits. Yeah, we're basically doing everything we can to meet the SpaceX requirements and go as fast as possible. Also, we're focusing on a cooling system. Currently, we're researching different cell chemistries and cell types and packaging and figuring out what to do with all this heat that we're going to generate, because we're going to go very fast. Yeah, I went through it all really fast, but that's basically it. There's a little bit more. I mean, controlling an induction motor is extremely, well, not extreme, it's complicated, but our test setup is going to allow us to figure out the optimal control drive frequency. Because that's the thing about an induction motor is the drive frequency is different than the actual frequency, and there's an optimal drive frequency for maximum torque. And so from the torque equation, there's a local maximum calculus. You find that, and it's just based on the actual drive, the rotor frequency, your velocity. And so I have formulas for this, but they require constants. So this test inverter that I've created, 5 kilowatts, small, but it's a test inverter. It should allow us to enumerate these control constants for our final inverter, which should have a power stage of over 600 amps. So yeah, that's basically the power system for OneLoop. Thank you.
All right, thank you so much, Ryan and Team OneLoop, for presenting on your power system and control system. So yeah, we're going to begin the presentations for the brake structures and safety setups, which is our last session for today at 3:20 UTC, so in about 6 minutes. So yeah, keep asking questions on Slack. Ask any questions on the Zoom if you're on here. And all your teams that are presenting, please get ready. Okay. Thank you so much for taking a good break, I guess. Let's get ready for the session on brakes, structures, and safety. So the first team that's going to present in that section is going to be OneLoop. So they had a section on both structures and brakes. So they have a 10-minute time slot, and then Cooper Union will be right after them. So yeah, OneLoop, you have the floor.
All right, let me share my screen real quick. All right, hello, my name is Jordan Hall, and I am one of the UC Davis OneLoop brakes team, and I'm going to be discussing a little bit about our braking setup. So the POD's braking system will be utilizing 4 sets of permanent magnet arrays, 2 in the front of the pod and 2 in the back. Each array will consist of 17 neodymium magnets with the highest possible grade N52. Each magnet will be about 1.5 by 1.5 by 1.5 cubic inches and will be oriented in a special orientation called a Hallback array. That way we can optimize our braking force. These magnets will be sealed inside an aluminum enclosure, which will be linearly actuated into operation by pneumatic pistons. So magnetic braking works by inducing a force called eddy currents, and eddy currents are formed when a magnet is translated horizontally against a paramagnetic metal, such as aluminum. These magnets must also be very close to the metal, since force drops with the square of the distance to the beam. To further optimize the magnetic force, the magnets can be rotated 90 degrees in respect to each other. Focus the magnetic field to one side of the array and negate the magnetic field on the other side of the array. And as previously mentioned, this orientation is called a Hallback array and is shown on the right. When drafting ideas for where to brake, there were 2 viable options. You could either brake on the top of the I-beam or brake on the sides of the I-beam. The original plan was to brake on the top because the stability system allowed us to actuate our arrays closer to the beam than on the other side. And this in turn would allow the arrays to generate more braking force. However, through simulations on ANSYS Maxwell, it was discovered that the arrays interact with each other positively if placed on the sides. And the interaction allowed one array to produce about twice as much force with the aid of the other array versus by itself. So pretty much each set of arrays could produce up to 4 times as much power, braking force power. Another benefit is that the forces orthogonal to the rail actually end up canceling each other out when the braking is on the side. And ultimately, the 4 arrays that we'll be using will be actuated 0.2 inches away from the I-beam, which is in turn a much safer distance than the 0.1 inches away on top of the I-beam. So permanent magnetic braking provided the most advantages over other different forms of braking. Braking on a brake disc, similar to how cars brake, is not very feasible with the velocity due to the heat buildup. The discs would actually heat up to that they would physically melt, compromising the entire braking system. Friction braking on the I-beam is also inherently risky because of the discontinuities of the track segments, and we don't want to take those chances of accidentally tearing a piece of the pod off. We also considered using electromagnets, but they have more sources of failure when compared to permanent magnets. They also require a lot of power, which requires a lot more weight. Permanent magnets also do not build up significant amount of heat, do not require physical contact with the track, and only need power to actuate them into position. So this leads us to the safety of the braking system. As I previously mentioned, the magnets will not touch the I-beam at all. And in fact, no piece of the braking system will ever touch the I-beam in the run. Heat buildup is also not going to be an issue with the brakes because we won't be in contact with the I-beam. Also, to ensure that the pod comes to a safe and reliable stop, 2 independent double arrays will be set up, one in front, one in the back, like I mentioned. And each single double array will be able to stop the pod by itself without the aid of the other. So data collection for this year has been made much more complex due to COVID-19. And under normal circumstances, the brakes team would be divided into 2 smaller teams, with one team conducting computer simulations and the other team verifying those simulations with physical test data. However, we had to suspend the collection of physical data in March due to the coronavirus. So the team has thus been performing simulations using the software ANSYS Maxwell. And with ANSYS Maxwell, a model of the I-beam was made. So factors such as magnet layout, grade, quantity, and distance from the I-beam could be optimized. So an interesting relationship that the team discovered during our simulations was between magnetic force and velocity. The graph below illustrates the force versus velocity data for a single double array at every 5 meters per second increments up to 180 meters per second. Force comes out at around the 10 meters per second range and then begins to slowly decline as velocity increases. So when the deceleration phase begins, the pod will initially decelerate pretty slowly, but that deceleration will increase as velocity decreases. And the pod will then hit its maximum deceleration at around 10 meters per second. Looking towards the near future, the brakes team plans to resume the collection of physical data to verify the simulations beginning in early October. Plans to begin manufacturing magnet array enclosures in pneumatic systems will also commence. We are also in the process of continuing our ANSYS Maxwell simulations on a cloud computer so we can produce even more detailed simulations in a quicker time frame. This concludes the overview of the one-loop braking system. Thank you.
All right, time for structures from one loop.
Gabe, you here?
Hi. Give me 1 second. Let me share my screen. All right, so I will be presenting on behalf of Dominic and myself, the other structures co-lead. So let me go ahead and get started. So our primary goal was to design a lightweight chassis. And in doing so, that would be hopefully increasing the speed of our overall pod when it's traveling through the tube. So to do that, we decided to use carbon fiber sandwich panels. And basically, this is a carbon fiber layer, a couple of carbon fiber sheets. And we use some epoxy to cure that to a core structure. The core structure is a lot lighter weight. This gives a strong overall structure, being the sandwich panel itself, while maintaining a lightweight structure at the same time. The maximum stresses obviously occur almost all the time at the surface of the structure. So having that lightweight core really doesn't affect our ability to withstand these kind of stresses. Yeah, so sandwich panel, it can be used as carbon fiber with a lightweight foam core. We will be using carbon fiber with a end grain balsa wood. As of right now, that's what we're going to be going with. And this is our unibody design that we have right now. Basically, this is a sandwich panel with two sandwich panels on the opposite sides. They're being attached via these slots that you see on the side there. That will fit together, and we also have bracing on the inside of the inside of the chassis, as you can see at the bottom there. So those braces basically will prevent any kind of overall failure of the chassis due to the braking and propulsion forces, the lateral forces that those cause. And our current dilemmas right now are both modeling the chassis as a single body in ANSYS. This actually proved to be pretty difficult given the fact that we have different materials in a sandwich panel, and ANSYS Mechanical doesn't really like having solid bodies of materials. You have to insert them as a two-dimensional surface and extrude that. And also fabricating a actual unibody core as we have it pictured in this design. That would be pretty difficult just because a end grain balsa wood would need some woodworking skills to actually create a design such as this. And none of our members really have that kind of experience at the moment. So fabricating that in-house would definitely be a challenge. So yeah, these are our two dilemmas right now. And that is all from the structures team at OneLoop.
All right. Thank you so much to the structures team and to the braking team from OneLoop for presenting your work. If you have any questions for them, please leave it in their channel on Slack. Also, I forgot that they also have a stability system that they need to present on, so they're going to be presenting on that at 3:50 after the last team, or whenever the last team presents in that session. So now it's going to be Cooper Union. Cooper Union, you have the floor to present on your work in this area.
Hello. Hi. My name's Daniel Kim. I'm going to be presenting on behalf of the Cooper Union. Here's my screen. Let me know if you guys see it.
Yep.
Okay, so our paper focused on eddy current brakes and simulation and modeling for it. So we spent the summer looking at simulation options and looking at the physics behind eddy brakes. So eddy brakes, as if you guys don't know, is a phenomena that occurs when there's a changing magnetic field in that passes by a conductive material, and it arises due to one of Faraday's laws, which is here, and so we took this equation and we wanted to look at how a lot of simulation packages deal with eddy brakes. So we started with this level 0 model, and we have like this geometry of a magnet passing by a conductive material, and we started with these 3 key assumptions where the magnet had a constant magnetic field, there was no air gap between the magnet and the rail, and that J equals 0 if not along the skin depth. And then with those 3 assumptions, we were able to find this simplified expression for the force here. And then the results of this can be found later in the paper. So we move on to see that a lot of like finite element analysis actually uses these PDE solvers to be able to solve eddy current simulations, and the equations that they use are here, and then in like a magnetic vector potential version that is here. So these are Helmholtz equations, and they're like very solvable and known. So it's very nice that programs such as DL2, which is an option that we looked at, and I think FEM uses this equation in the background. So it was nice to be able to find this. So yeah, so here is a result. One of the considerations we had was the skin depth and how skin depth changes with the velocity of the pod. But even at 200 meters per second, the skin depth is about 0.5 meters, and that's much larger than any anything that we will be dealing with in terms of braking. And here's the results of the level 0 model. And then here we have a result of braking force with and without back iron. And back iron is just a material that allows the magnetic flux to return back to a braking system. And with back iron, you can see like the force is almost doubled. It's interesting because another option we were considering was Halbach arrays, which is just a configuration of magnets that increases the magnetic flux on one side while eliminating it on the other, basically. This is this simulation of the Halbach array magnetic field versus a normal array of magnets. And as you can see, there's much more flux on this side than this side. And what's beneficial about that is that not only is there more flux on here on this side, but you don't need a back iron on this side to be able to bring the flux back into the brakes, because the Halbach array has its own shielding effect, as they call it, that will bring it back into the working side. And here we have some derivations and conclusions. And yeah, we plan on looking more into DL2 and ANSYS and COMSOL, and we're going to see which option is going to be the best for the future of our Hyperloop braking system. That'll be it.
Awesome. Thank you so much to Dan and the team at Cooper Union for their work on this topic and on braking. Next up, we're going to have HyperExcite from UC Irvine. That's going to be presenting on their braking and structures work. HyperExcite, you have the floor.
Okay, let me share my screen. Oh my gosh. Okay. Hi everyone, my name is Mahak. I'm the project manager for HyperExcite. And my name is Lana. I am the braking lead for HyperExcite.
And I'm Karan Patel. I'm the lead piping and cooling engineer on HyperExcite.
Okay, let's get started. Okay, so as Myron introduced our team, we've been a team since 2015, and I just wanted to highlight that the systems that we'll be talking about are the braking assembly and the pneumatic assembly in the top left and bottom left of the figure on the right. Next slide.
Okay, so I'll be going over the reasons why we made our changes to the pod. So as Myron has said before, we're actually moving down to a smaller scale pod for a more R&D year. So for pod 4, the braking mechanism was a permanent magnet eddy current braking system with 2 Halbach arrays oriented on either sides of the I-beam flange. So it's no contact. As you can see, we did some ANSYS E&M field strength profiles just to make sure that we don't have like badly oriented magnetic profiles. And then you can see our lift and drag profiles, and our highest drag was about 2,700 newtons of braking force. So for pod 5, we're actually moving to a pneumatically actuated friction braking system with a maximum braking force of about 1,574. So if you look at figure 1, that's the entire braking mechanism, which can then be broken down into, as you can see from figure 2, 4 braking sub-assemblies, which all clamp onto the I-beam. So since this is contact braking, there's more of a concern about the stresses and the forces going through the braking system. So we've done some analysis in ANSYS on on specifically our brake pad plate, which is the part that would be clamping onto the I-beam. So as you can see from figure 3, that's our simulation. And then we also did some hand calcs, as you can see from the second figure 2 in the bottom left-hand corner. But we have a minimum structural factor of safety of 6.4, which is much higher than SpaceX's requirement of a minimum structural factor of safety of 2. And our stepping rate is about 2.95 Gs.
So within the scope of the braking system, since we are using double acting actuators, the purpose of our pneumatic system is to provide air pressure to the actuators to engage and disengage those brakes. But alongside that, our pneumatic system also builds in a redundancy that automatically engages our brakes in case our pod loses power for any reason.
Okay, so in the parts, going over the system, we start with a compressed air tank, and then we have a pressure transducer and a relief valve pressure regulator going down. And we wanted to put the schematic to highlight that in the system, there's a manual shutoff valve as well in the middle right of the system. That whole system is manual shutoff. And then as you go down, there's a 5-2 solenoid valve below the low pressure accumulator tank. And this is basically the main component and acts as the main redundancy in the system. And it helps actuate the brakes. And like Karan mentioned, there are 2 modes, pod on and pod off. And we have to make sure that in the event that there's a power loss for whatever reason to the pod, that the pod stops. And so the 5-2 solenoid valve will be programmed in a way that the brakes will be engaged when the pod is off. Next slide.
So when comparing pod 4 and pod 5, when we consider feasibility and designing a fail-safe mechanism, one stark difference in the fail-safe system is that because pod 4's brakes were a permanent Halbach array, the fail-safe was built into the braking system because the braking system was more mechanical. But now that we're using pneumatics to power the braking system, we had to factor in a pneumatic redundancy so that, as Mahek said, it's programmed in such a way that if there is a power loss for any reason, the brakes actuate immediately.
So in terms of comparing between pod 4 and pod 5, since we are talking about wanting to downscale on the weight and the cost to us, you can see from pod 4 to pod 5, we went from a like 30 kilogram weight to a 17 kilogram weight. And the cost of having like buying Halbach arrays and then manufacturing the braking design around them is that Halbach arrays themselves are incredibly expensive. So taking into consideration the entire braking system, it was $9,500 just for the arrays. And then with the rest of the structure, it was $12,000 just for braking, not even taking into account pneumatics. So we moved down as we moved to a friction braking system, and we focused on more off-the-shelf parts and more on designing around what we have. We went down to 1,000 for braking and 1,000 for about 1,000 for pneumatics. So in conclusion, when comparing the two, pod 4, it costs about $4.50 per 1 Newton of braking force, while pod 5 is only $1.29, which is significantly cheaper for us, especially since we're talking about a more R&D year. And then we've also cut down significantly on the weight. Pod 5, our pneumatic and braking system together, is about 16% the weight of pod 4's braking mechanism, or sorry, 50% the weight, and then 16% the cost of pod 4's braking system. So in terms of thinking about what's good for the team and what's good for our actual design, a pneumatic friction braking system was best for us. And that's it.
All right, awesome job, Team HyperExcite, on your presentation about your structural work and braking work. Now we're going to turn it over once more to Team OneLoop, who will be our last presentation for today, and they're going to be talking about their stability system. Once again, if you have any questions you want to ask, please go on the Slack and leave those so we can discuss them after this presentation. Thank you. Oh, and OneLoop, you can go ahead whenever you're ready.
All right, thank you. Let me share my screen. So, hi, my name is Jovan. I am one of the stability leads in OneLoop, and I'm going to be talking about OneLoop's stability system design and analysis. So for this year, we opted to go for a complete redesign of our stability system. So we wanted to focus a lot more on simplicity and robustness. So we chose to go with a straddle type monorail design. So this type of design, which I'll show a picture later, has been shown to be really successful in previous competitions with many of the top performers in the 2019 competition using this type of design. And it's a tried and true method in existing transportation, the monorail. So we split our system into 3 main areas of research and development. So the first one is the design of the actual suspension mechanism, the design and analysis of the wheels, and also the development of a mathematical dynamic model of our stability system. So here you can see just a quick concept, just a simple concept of our stability system, the monorail design. So it's keeping with our goal of simplicity and robustness. We just decided to go with a simple force magnification linkage connecting the wheel and the chassis. The main part of this design is researching what types of shocks we're going to use. So there's the choice of, so first off, we decided to go with mountain bike shocks. There's the choice of using either coilovers or air shocks. So with the traditional coilovers, They're very reliable. They've been used for many years, and they're very responsive. And it also has like a linear spring rate. It's what the spring Hooke's law comes from. But some of the downsides is the springs are made of metal, and it's heavy, and they're hard to adjust because the metal springs have just one spring value. The other option is to use air shocks. Air shocks are much lighter. They have they're very adjustable, and they also have a progressive spring rate, which in our case is actually very useful. However, with this being Hyperloop, we might have we don't know how it might behave in a vacuum since it is powered by air pressure. So further research needs to be done to determine exactly what geometry to use for our linkage mechanism and the spring constants and how the shock behaves. So for the wheels, since our structures team that presented earlier was going to use carbon fiber, we decided to also utilize that carbon fiber to manufacture our wheels. So our wheels are going to be manufactured in-house using a carbon fiber composite. And that cuts down a lot on the wheel's weight, which means we don't have to worry about the size of the wheel affecting the pod's weight too much. To maintain contact with the track, we're opting to use either rubber or polyurethane tires to both maintain friction with the track and also add a little bit of like spring deformation to deal with variations in the track. So for our research, we're looking on like properly sizing all of our components, such as bearings, wheel diameter, and shaft size to get our target speed of 350 miles per hour. And our next step is to research the actual design and manufacturing of the carbon fiber. Our third point of research is to come up with a sort of analytical mathematical model of the dynamics of our pod. So what we've done so far is we've split it up into a vertical stability simulation and a lateral stability simulation. So the vertical stability is based off of a traditional half-car pitch heave model. And we sort of calculated that using the bond graph method. And we simulated it in MATLAB, which gives us some preliminary values for displacement. And the reason these simulations are so useful is because as our pod continues to develop and iterate, we can easily change all of our parameters that we have in our simulations to update our suspension accordingly. So the lateral stability model is currently in development, but we're running into some trouble with that right now because there's not that much documentation that you can find online in research papers and stuff about the lateral stability. However, we are making a lot of progress in developing a full 8 degree of freedom model, which is using just a different method than what we were using before. And this method we found is actually a whole lot easier. It's using Lagrange mechanics, which is a lot easier, and it will give us a more accurate and complete description of the dynamics of our pod. And yeah, so that is our stability system. Thank you for listening.
All right. Thank you so much to Team OneLoop for presenting on your stability system. So now we are going to, I think what we'll do is we'll take a 5-minute break just so that people can ask questions on Slack or on Zoom, or even for the folks who are streaming on Facebook, just so we can like have an idea of what questions to go into. So yeah, please ask away on those channels, and let me know if you have any questions. See you in 5.
تمام جاي
All right, and thank you guys for asking some really, really interesting questions and for some amazing presentations. Before we get into the questions, I just wanted to point out that if you want to participate in the voting, it's going to close at 10 p.m. today, UTC time. You need to go to our website, which is hardtechfund.com/hyperloopvoting.html. And here you'll see you'll see the link to our live stream. You'll be able to vote for your favorite presentation in each category. And then you'll also be able to take a look at the paper submissions. So the way that we're going to do this in terms of picking the top team for the panel is it's going to be a combination of the points that the team scores in the paper, as well as their presentation score. And the team that has the highest in both categories will be the team that presents in that panel. Now, obviously, like there are some panels that we already know who the leader will be just because there was only one team that submitted in that area. But for some of these sessions, it's definitely going to be very interesting to see who will be the top team. So for all of you who are researchers and stakeholders, please make sure you go and do this, especially the paper review, as your votes will also be counted more. So stakeholders and researchers will have their points be counted more than just any interested attendee or anyone who's going to the link and voting. So what also is going to happen is at 10 p.m. UTC, we're going to share out the feedback from every one of the teams to the teams that are participating so that they can see exactly how they can improve their section and get ready for the panel tomorrow. And if you have any questions on any of this, please feel free to message me or send me an email or anyone else on the Hard Tech Fund team, and we can discuss it and see how we can do it. But anyways, Q&A time. So I think the first question that that didn't get an answer that I think we should definitely talk about is it was asked by Gregor, and it was for teams that are running belt drives. What other kind of power transmission was investigated, and why was belt drive found to be the most suitable? Okay, who was working on belt drives?
Hello?
Hey, what's up, David?
Oh, hello. Sorry, I had my microphone muted. So for HyperExcite, we used a belt drive. The reasoning for that versus like a gearbox or a direct drive was because of the geometry needed when we're using our tension spring suspension. The geometry ended up being a little bit awkward for other types of transmission, and the belt drive ended up being the best way to get from the motor to the drive wheel as compact as possible.
Okay, makes sense. Makes sense. Then another question that I thought was pretty interesting was, how it was asked by Luke to HyperExcite. So Team HyperExcite one more time. How will your team mitigate risks and potential unknown variables associated with braking directly on the I-beam? I understand that at last year's Hyperloop competition, TUM's frictional braking system collided with the discontinuity between track segments.
Yeah, so for HyperExcite, we added a flange to our brake lining to hopefully mitigate any of the undue stresses or mitigate any chance of catching onto any discontinuities in the I-beam. The brake pads are also slightly longer, so if it's an actual gap in the track, it should, after it gets over that initial bump, be able to glide across. We also rely a lot on our stabilization. So if the brake pads can get over, then it's up to our stabilization to mitigate the oscillations that come from that. So yeah.
Cool. Thank you for the explanation on that. And then another question that Gregor had asked to OneLoop was, does the dynamic model take chassis and mounting flex into account? Oh, I see Jovan already answered it. Did you want to explain a little bit more, Jovan?
Yeah, so basically the goal of our dynamic model is basically, because right now our pod is still very early in development, so nothing's really set in stone yet. So what's really nice about a dynamic model is that we can change our parameters as much as we want and really quickly get an idea of how our pod will move and perform. Further on into our development, once we have more of our systems more properly defined and more designed and CAD'd up, it'll be a lot easier to just throw it into ANSYS and perform a FEA on it instead. Hope that answers your question.
Yeah, sounds good. Thank you for the explanation, Jovan. And then, I mean, I see Gabe typing the response for this, but Gabe, if you want to answer this for OneLoop as well. Sam from Strathloop had asked, for your carbon fiber sandwich panel research, how have you designed and tested the panel strength to shear loading? And how are you modeling the epoxy structurally to validate against panel delamination?
Yeah, so I actually just sent my response in the chat. But basically, so we have performed some finite element analysis in ANSYS on the chassis. We've yet to do it on our unibody design. However, we have performed some physical testing of a sandwich panel using a foam core. And that did decently. It definitely was a good learning experience. And ideally, we'd want to use at least 4 to 5 sheets of carbon fiber. That seems to be working the best. At the moment, we haven't really came up with a way to prevent delamination. I know in our physical model, we taped off all the edges of the carbon fiber to prevent fraying. However, delamination wasn't completely looked into yet. But when we do figure that out, I could definitely reach back out to you guys.
That sounds good, thank you.
Yeah.
All right. Well, thank you everyone so much for presenting today. And thanks for everyone else in the community who has participated in providing some strong feedback and in helping in the Hyperloop community over the last few years. Like I had mentioned before, please go to our website, hearttechfund.com, go to the Hyperloop voting section to vote on your top team by 10 p.m. UTC today. Yeah, please leave any comments, questions, feedback on this Facebook post or on Slack, and we'll be sure to get out to you. Going to end the live stream now. Thanks.